Well, we're not doing any kind of videotaping today. Today we're working out on the fly an outline for our next article, which will be a realistic simulation of polarization transport phenomena in 1 cubic nanometer of water. I'm going to try to reconstruct from scratch how polarization transport works in frozen water with and without a gradient. So let's go kind of off the top of our heads. Let's take stuff that we think is reasonably immutable. First of all, the sample density. We're going to call that rho. And we're just going to take a guess that rho is 1 over L, where L is a length scale. And I'm going to set that L, I'll use a small l, and I'll put a p on it for proton. And I'm just going to take a guess that LP is on the order of 2 angstroms. Next, we're going to have a spin magnetic moment. The spin moment is going to be h bar gamma over 2. And how do I know that? I just know that the Hamiltonian classically is the magnetic moment times b. I know that quantum mechanically it's h bar gamma times the spin operator. It's gamma times the spin operator, and h bar gamma over 2. The 2 is spin 1/2, and I just know that. Then I'm going to do the RMS dipole field. And I might not get the factors of 2 right. Let's see, mu0m has as units of B. M has magnets of mu p over L cubed. And I remember there's a 4 pi. And there might be like a 2/3 or a 2 or something like that, and that I can work out later. So I know that B RMS, it's not a vector, of proton to proton is of order mu0 over 4 pi times mu p divided by LP. Okay, and why don't I just, where gamma p is of order 40 kilohertz, per millitesla. And my recollection is that this is going to be around 1 millitesla. And now we're actually going to take a minute, and I'm going to check that on my Mathematica notebook. The exchange time. So how long does it take polarization to swap between two protons? I'll call that R exchange. And that is going to be gamma p times B PP. And I can look these up right here. This is around 0.1 millitesla times 40 kilohertz per millitesla. So it's going to be around 0.2, around 8 kilohertz. So I'll call that 10 kilohertz, which is, so it's about 10 times times 1,000 times per second, so it's around 10 to the 4 per second, which is 1 over 100 microseconds. So that's going to be the time scale on which 2 spins exchange polarization. So if this spin is up and the other spin is down, we wait 100 microseconds, they'll have swapped over. Okay? Now, from that, what is the diffusion constant? Well, the diffusion constant that has units of length squared per time. And the only length we have is LP. And the only time we have is 1 over the relaxation. We already know the relaxation is 10 to the 4 per second, and L squared is, well, let's just see how far things can go in 1 second. So the diffusion distance is going to be, and I'll call this D. Well, that distance is going to be proportional to D. It's going to be the square root of D. Times the time, which is 1 second. In 1 second, this rate times the time is 10 to the 4. The square root is 10 to the 2, so this is going to be 10 to the 2L. L is around 0.2 nanometers, so in 1 second it's going to diffuse around 100 times 0.2, 20 nanometers. So that's how far nuclear spins will diffuse. Now, electrons will diffuse a lot faster because they have this much bigger moment. But on the other hand, they're much farther apart. So I'll have to work them out for RICO, but we can adjust this D to be almost anything that we want. Okay, so one of the challenges in dynamic polarization is that 20 nanometers in 1 second is not, really a tremendously long distance. However, the nice thing about MRFM is that relative to our slices, which are only 2 nanometers thick, that means it will diffuse a 2 nanometer thick slice. It will diffuse that in about 1/100th of a second. So polarization transports that are slow on macroscopic scales are fast on our scales. So my gut feeling is that a D is going to be a bigger number than this, but not a whole lot bigger. That we'll be talking about simulation times of order, maybe 1/100th of a second.
So are you deriving all these numbers from first principles before my eyes?
Yes.
Or are you
Yes.
guessing that these will be the results of the simulation?
I'm deriving them before your eyes, but I'm not getting all the factors of 2 and maybe not even all the factors of 2 pi.
Yeah, my question was going to be, what's left for the simulation to do?
Oh, nobody knows if these hand-waving arguments are right. I mean,
so these are really guesses.
I'm assuming that each spin talks to just one other spin, but really each spin is talking to dozens of other spins.
So these are guesses or estimates made based on a kind of very simplified picture.
Hugely simplified. I mean, it wouldn't surprise, because there are what are called many body effects. Really, each spin talks simultaneously to dozens of other spins. What I really should do is not take the spin B, but I should assume that all the other spins are adding randomly. And it might be talking to say 50 other spins. If they add randomly, then I have to take the square root of 50, and then that would raise this exchange rate up by a factor of 7, and then I'd take a square root right here, and it might be another factor of 3. So we really might get more like the 60 or even 100 nanometers in 1 second. That's why I had in mind that this is probably an underestimate. T1 needs to be on the order of, well, the exchange is on the order of 100 microseconds, I would say T1 can be a millisecond. It needs to be bigger than a millisecond. The rank R needs to be, as T1 gets longer, I need more rank. As the rate gets faster, I need less rank, because it's all going to average to 0. So it's going to be RT1, which is about 10. So I don't think we need rank 100. I think rank 10 is going to do it. And I'm going to draw what I think the curve is going to look like. I'm just going to pick a T1. I don't yet know what it is. And I'm going to assume that, quantum effects make the simulation bigger. And I think this is what we're going to get. If we calculate D for a classical system, we get a simulated value that's too low. If we go to rank 2, we get a higher simulation. If we go to rank 10, we get an even higher simulation. And if we go to rank 100, we find that although the calculation slows way down, we don't get a different value. This is going to be, I'm going to set this for T1 equal 10 over R. Remember, T1 is an artificial noise. What if I made it even noisier? And I'm going to do another curve. I'll make it less noisy, 30 over R. And here I think we're going to get the very similar values. And then in red, I'm going to do a really quick and dirty simulation. This is going to be T1 equal to 3 over R. T1 equal 1 for R. So in the limit that we had a very long T1 and a very high rank, we're going to get the true value. But we're going to get surprisingly good results, even with a modest rank and a modest T1. The classical picture is actually going to give pretty satisfactory results and really, really fast. It's going to be right within factors of 2. This is not a logarithmic scale. And what I'll do here is I'll put some error bars on here. I do know this. A point out here takes 100 times as long to run as a point down here. So we're not going to get a lot of statistics. We're going to get tons of statistics here and not much way out here. So this is going to look just like a fluid dynamical simulation where we do a few runs with a very small finite element and longer runs with a finite element. So what a good time for me to write a conclusion here. We observed that rank R equal 10 sufficed for RT1 greater than or of order. That would be the most optimistic solution. That I'll just say of order 3. If we set T1 to a value as short as 3 and rank as low as 10, that we can operate in this sweet zone of minimal rank and longest possible T1. Now, how good does our diffusion estimate need to be? I'm thrilled if we're within a factor of 2. Absolutely thrilled. That's like estimating the drag coefficient of turbulent flow within a factor of 2. I would rather have 10 simulations right within a factor of 2 than 1 simulation right within 20%. So, and that's going to be the kind of trade-off that we're